examples 7 through to 9b on these particular boards. We've moved on to linear equations, which should be very familiar to you, all the way back to equations of a straight line given 2 points. So basic information, question 7, 2 points, -1, 4 and 2, 7. We need to find the equation of the line. To do that, we'll need to find the equation of the slope of the gradient. So you have a formula, rise over run, delta y over delta x, but y2 minus y1 over x2 minus x1. Substitute in points, be careful with the directed numbers again. Use the brackets. Not great mathematical working here to work across the page, but a little bit short on space. And I also quite like seeing the working out on the top, on the numerator and on the denominator. So I don't mind that particular approach for that particular gradient function. Or gradient, finding the gradient there, sorry, I should say. Second part of this work is to use the equation y minus y1 equals mx minus x1. Now you'll notice I haven't used point 1, I've actually used point 2. x1, y1 is just a coordinate. I happen to label this one, I happen to label that one 2, but any coordinate will do. Now my choice of point 2 means I won't have to deal with the negative number here. So x2, y2 is what I'm using for x and y in that particular equation. Very familiar work, tidy it up, y equals x plus 5. I will show you at a later stage a CAS program that I've written that will basically give you an opportunity to just put the 2 points in and it will spit out the equation for you. Very useful for those students doing further mathematics as well. Moving on to again another familiar concept that we're going to use extensively in methods 3-4, which is domain and range. A couple of things to note here, the use of the closed circle and the open circle, so be careful with your brackets. Obviously a closed bracket, a square bracket for a closed point, and an open circle, an open point doesn't include the point 3, would be a round bracket. The other thing to be careful of is that you always go from smallest value to lowest value. Very easy to mix these up and go from left to right on the graph, but you need to go from the lowest value. So with your y values, with your range, you're working up the page. So the lowest point is -5 up to a y value of 2, and your domain, you're working left to right, -4 to 3. So make sure you get those in the correct order. No real tricks there. Parallel lines and perpendicular lines are covered in question 9, and the bits of theory you're going to need there is information about gradient. For parallel lines, m1 equals to m2. When we get back next year, we'll have a look at a few varieties of this where we actually look at the y-intercept as well to see if the lines are parallel or actually coincident, as in the same line, but that's all next year. So we've got our 2 equations here, and I'm looking to try and find what values of A will give us the same gradient. So you can see here, by the time I rearrange this equation here, I get down to the form y equals mx plus c, and I'm going to do that for the second equation as well. Just a little bit of notation that I'd like you to follow through this particular course here. We're going to be working with multiple equations, multiple representations of the same equations. So my notation here is a good one to follow. Equation 1, equation 2, I've set myself up. Now equation 1 dash and 2 dash, or 1 prime and 2 prime, have not actually got anything done to them other than some rearrangement. So it's different to equation 1 only by the fact that I've rearranged it, I've transposed the equation. So it still stays as equation 1, but a new variety, so it's 1 dash and 2 dash. Now I've got those into the same form. You'll also see some of the set out here. I like to keep it all aligned, so x's were here, y's were here. So if I'm looking to transpose, my x's have moved across, my y's have stayed in the same position down the page, so my set out is nice and neat here. Once I've got this here, again with the colour coding, it's very easy to see y equals mx plus c. At this stage, not interested in the constant there, and y equals m2 plus or minus some c value, and we're looking to equate those 2 values. So when minus a, the slope of the first line, is equal to 2/3, the slope of the second line, we will have the same gradient. So solving that little equation, minus a equals 2/3, therefore a equals -2/3 will be the value used in that equation there, would make those 2 lines parallel to each other. Similar bit of work with perpendicular lines. This time the bit of theory you're going to need is the perpendicular lines that cross at right angles. Either of these forms, we'll start with this one over here. The 2 gradients, because they meet at right angles, the gradients will multiply together to give -1. Now the variety that you may be familiar with is that the gradient of a normal is -1 over the gradient of the tangent, and vice versa. So in practice we change the sign and we also flip a fraction as well, and we'll see that in practice in a minute. So taking the 2 equations, 1 prime and 2 prime from the first example, sorry, -a x plus 7, and 2/3 x minus 4/3. Well, these are the two parts we want to obey this particular rule for perpendicular lines. So I've chosen this variety here. I've substituted in m1 and m2. Minus a times 2/3 should give me -1. A bit of work with your fractions, and you'll see that a equals to 3 on 2 by solving that particular equation. What I talked about before in terms of changing the sign, so negative becomes a positive, and we're going to flip that fraction as well. So 2/3 becomes 3/2, and that gives us the value of a, which for this equation would make those two lines meet at right angles, 90 degrees, perpendicular lines. So that covers content from equations of 2 points, gradient work, y1 minus y1, y minus y1 equals m, x minus x1, domain and range, parallel lines and perpendicular lines. Next up will be examples 10 through 14.